So, friends, welcome to the lecture 46 of the course Advanced Steel Design. We are now going to continue to learn curved beams with large initial curvature. I will put as 2. So, in this we are going to find out the expression for stress at interdas and stress at extradas. So, in the last lecture we said that the integral I is y square plus ye by r plus y dA, which we split into integral y square by r plus y dA plus e times of y by r plus y into dA. We call this as I1, this as I2, and I1 was for the split because this can be rewritten as integral of y minus ry by r plus y of dA. You can multiply and see, you will get the numerator as y square. Okay. Now, this can now become I1 can become split as two integrals y dA for the area A minus r times of y by r plus y dA over the area. Am I right? This is where we left, and I hope you would have done the integration by this time and substituted back in the original equation. You must have got the I value. Let us continue from this point. So, now integral y dA for the entire area A should be 0. Why? We are assuming that the geometric axis and neutral axis coincide. So, I will be I1 plus I2, which is so this goes away. So, minus r, I am copying this integral y by r plus y dA over area A plus, then I am copying this integral plus e times of y plus r plus y dA for the area A. Furthermore, friends, we already have this relationship with us. If you recollect, we have this integral y by r plus y dA for A is called as MA, which has dimensions of area. Okay. Having said this, the integral now I becomes integral y square plus Ey by r plus y dA okay. This is the original integral we had, is it not? This is the original integral we had. Okay, which now can be expressed as minus r of MA okay, plus E of MA. Can I say that? Because this is also MA. Okay. So, now I can say this integral is now going to be minus MA times of R minus E, equation 12. Now, substitute equation 12, this equation 11 we had, okay, substitute equation 12 in the moment equation. What is the moment equation we had? Please turn your notes. M was equal to minus E del phi by del phi M A R minus E. Am I right? Okay. So, now I have substituted this integral back and got a new equation for M. So, now I can say E times of del d phi by d phi should be equal to minus M by M A of R minus E. Am I right? So, please understand this equation. This is the applied moment. And this is cross sectional property. So, do not get confused with the notation M. We also know that M is given by minus E by R minus E. I think this was equation number 9, please check that. Okay. So, I have somewhere MA here, let me substitute that. So, therefore, E del d phi by d phi yes now become M by, okay. So, let us say okay minus M by MA R minus E, which is now minus M by minus EA by R minus E into R minus E, which will become M by AE. Am I right? So, therefore, friends, E del d phi by d phi has become M by AE. The small m have gone, we have substituted back. Equation 13. So, substitute this in equation for the stress. Substitute in equation for finding out the stress. It was possibly equation 4, you can check that. So, the stress is now given by M by AE times of Y plus E by Y plus R. This was actually equation 4. Also, E is M by M minus 1 of R. Hence, stress now becomes M by AR M minus 1 by M Y plus M by M minus 1 of R divided by y plus r. I am just substituting, okay. Okay. Further simplify, stress is m by ar m minus 1 by m, okay, that is what we have here, m minus 1 into y plus mr by m minus 1 into y plus r. Okay, let us now remove this. I get stress as m by ar 1 by m of y plus r minus y divided by y plus r. Am I right? This is stress value. So, now I can write stress is given by m by ar 1 by m y plus r minus y by y plus r, which can be further simplified as m by ar 1 minus, okay, 1 by m of y by r plus y. Can I say that? The classical equation we have for curved beams, which is equation 15. Let us copy this equation . I am copying this equation to the next screen. Okay, where we know where m is the applied moment, in such a manner it reduces the curvature. A is the area of cross section of the member. Sigma is the tensile or compressive stress at a distance y measured from the centroidal axis Now remember, y is measured from the centroidal axis, not from the neutral axis. That is a common confusion people will have. Generally, in classical equation of bending, for finding out stresses, the distance of extreme fiber is measured from the neutral axis, but here it is from centroidal axis. Please understand this. It is a very important deviation we have. Okay. Then of course, r is a radius of initial curvature, we should say, of the unstressed beam, before the M is applied. The moment is applied, okay. Original initial curvature. Friends, this equation 15 is classically known as Winkler-Bach equation. equation 15 is classically known as Winkler-Bach equation. Okay, Winkler-Bach formula or Winkler-Bach equation. Okay. So, I think we have derived the stress to be found out at any point distance y from the centroidal axis if I know the geometric properties of the curved beam and the value of the applied moment acting on the curved beam. Am I right? Let us revise some sign conventions. For curved beams. Let us say the equation is very generic. Stress is given by m by AR 1 minus 1 by m y by r plus y. Now, y is measured from the centroidal axis. Okay. It is negative when measured towards the concave side. It is positive when measured towards the convex side. Now, one will have a confusion. What is the convex and concave side? So, in a given curved beam, okay, this is convex side called extradas. This is concave side called intradas. Okay. From the centroidal axis xx, when you move towards this, y is positive. When you move towards the convex side, okay, let me write it clear, towards the convex side, towards the concave side. Okay. Right. So, let us apply this condition and try to find out the equations for intradas and extradas. We also have an alternate equation for stress. Stress is also given by m by AE y plus E by y plus r. If you remember, we derived this equation. This was equation number 14. We derived this. So, using this, stresses intradas will be m by AE E minus HI by R minus HI. Look at the figure. HI is the depth of the intradas point measured from the centroidal axis. Okay. I can rewrite this equation as, which is equal to minus m by AE of HI minus E by, look at the figure and see what is R minus HI. Can I write this as RI? Negative indicates this is compression. So, intradas will have compression. Compressive stress. Okay. Let us do it for extradas. Sigma O will be m by AE y plus E by R plus Y, which is m by AE E plus H naught by R plus H naught. I am looking for the extra point. Okay. So, I am substituting this as H naught. Okay, that is what I am doing. So, that is going to be plus m by AE H naught plus E by R0. Can I say that? So, this is tensile because it is positive, and extra DOS has tensile stress. That is what we also plotted, isn't it? The plot was like this. So, this is all compression and these are all tension, is it not? Am I right? So, it's 14b. So, this was 14a and this is 14b. Let us look at a limiting case. Curved beams with large initial curvature can also become a straight beam when R tends to infinity. In such condition, the stress expression should reduce to the form m by I into y. Isn't it? That is a classical thing for a straight beam. Let us show how this is happening. So, we know stress is m by AE y plus E by y plus R. Now, we know E is minus mr by 1 minus m. So, stress now becomes m by minus mar into y plus E of 1 minus m by r plus y. Okay. Now, for a straight beam, E is 0, is it not? That is, there is no shift of neutral axis from the centroidal axis. Shift is 0. Okay. Hence, small m will become 0 as R is infinity. Therefore, stress now becomes minus m by mar y by r plus y. Okay. Further, integral y square dA by r plus y will now become integral y minus ry by r plus y of dA for the area A. We also know integral y dA for the area A is 0. Hence, this will now become minus r times of y by r plus y of dA for the area A, which will now become minus r times of MA. Hence, the stress equation now minus mr by mar y by r plus y. Okay, which means stress is m by integral y square by r plus y dA into y by r plus y, which means stress is my by 1 plus y by r of integral y square dA by 1 plus y by r for the area A. Now, since r is infinitely large, the above expression will now reduce to the following form. Sigma is m into y by I, where I is y square dA second moment of area, which is applicable to straight beams. Now friends, there is an important statement here. M is a sectional property, which is to be developed or which is to be estimated for different cross section shapes used as curved beams. Okay, so that is the job we have additional. Okay, let us do that now for one or two and see how they can be estimated. So, now we are looking for estimating m factor. Which is otherwise called as modified area. How it is modified? You are applying a moment, it changes the curvature, the area is getting modified. So, where it is being used? In the stress equation. See the equation we have for the curved beam, 1 minus 1 by m y by r plus y. So, this is the factor of the cross sectional area. So, it is a geometric shape dependent factor. Okay. Furthermore, y is measured from the centroidal axis, not from the neutral axis. You must remember this. Okay. There is a common confusion and a common mistake which people generally make when you estimate stresses. So, we will take up an example of a rectangular section. Draw a rectangular section. We will say this is my reference plane from where I am going to measure the curvature. Remember, Beam is a curved beam, the cross section is rectangular. Okay, please don't get confused. I should say rectangular cross section. Okay. So it has got the centroidal axis. As usual, the centroidal axis will be measured from OO at distance r, and if I have this as my width and this as my depth h of the cross section, we know this is indicated as R1 in our nomenclature and this is indicated as R2 in our nomenclature, and from the CG this is HI, which is h by 2, and from the CG this is HO, which is h by 2 again. Okay. Now let us consider a strip at a distance V from here. Let the thickness of the strip be dV. The strip is measured at a distance y from the centroidal axis as usual. Okay. Y is positive when it is measured towards a specific extrador side, we know that. So, the equation for MA is integral y by r plus y dA for the area. This is general equation here. Let us find out what is dA in this case, the hatched area. Can I say the dA is B into dV? Can I say that? Now, MA becomes integral for the area A y by r plus y dA, which I write this as, can I write y as V minus r from the figure? Can I write r plus y as V from the figure? dA for the area. Okay, this has got plane of reference. With which the curvature is being measured. Okay, I think this is okay. MA is given by this. So, now furthermore, MA is integral V minus R by V of dA, that is what we have here. I have written the same equation. I split this integral into two parts, which is integral dA for A minus R 1 by V dA, am I right? Which will now become integral dA for the area A minus R dA by B, which runs from R1 to R2 from the figure, am I right? Which will be integral dA for A minus R times of, we already have dA here, which is B dV, can I say that? So, B dV by 1 by V is here, by V. So, therefore, MA now becomes A, because integral dA over A is A minus RB Rn. So, the limits are R1 to R2, R2 by R1. Okay. So, which says MA is A minus RB ln. What is R2 from the figure, friends? It is R plus H by 2 minus R1 is R minus H by 2. Can I say that? So, now I can write MA for a rectangular section as 1 minus R by A times of b of natural logarithm of r plus h by 2 by r minus h by 2. This for a rectangular section. Okay. Let us derive it for a circular section. Let me draw a circular section. Let me draw the plane of reference. Let us mark the critical points. We say this is my centroidal axis as usual. And that is always measured at distance r from the plane of reference. Let me mark the neutral axis at a distance e from the centroidal axis towards the center of curvature. Let us mark a strip at a distance y measured from the centroidal axis. Let us say this strip is at a distance v from the plane of reference. Let us say the thickness of the strip is dv. Is it not? And let us say this is small r and this angle is theta. We have the equation MA is integral y by r plus y dA. We have to use this over the area E. Now, let us find out what is dA. dA is going to be the width of the strip. Okay, we call this as dy. Okay, width of the strip, which will be r cos theta into 2 into dy. What is y? Can I say y is r sin theta? In that case, what is dy will be r cos theta d theta. So, now dA will become twice r cos theta d theta, which will become 2 r square cos square theta d theta. That is my dA. Am I right? Having said this, MA is integral y plus r y dA for the area A, which will be integral v minus r by v of dA, because y from this figure can be v minus r, y from this figure v minus r. Can I say that? And r plus y is of course v, right? So, I am using it here. Now, this will reduce to the form integral dA for A minus r 1 by v dA, which will be A minus r 1 by v dA for A. This is my MA. Am I right? So, now let us pick up this integral, which will be dA by V y. We already have an equation for dA, does not? Let us substitute that, which will be 2 r square cos square theta d theta divided by r plus y, the integral for the area A. But now the variable is changing, okay? Theta is the variable now. So, theta has to now vary from minus pi by 2 to plus pi by 2. I am covering the whole section. So, which will now become minus pi by 2 to plus pi by 2 to r square cos square theta d theta by r plus r sin theta, because you see y is also changed. Okay friends, it is a very interesting integral, which is dA by V integral A. We will stop here. I want you to evaluate this integral. I will continue this in the next lecture. Okay. So, friends, in this lecture, we understood the stress equation for beams with large initial curvature. We understood that MA is a modified area, is a cross section property. So, we need to find this M factor for all cross sections, which are commonly used for curved beams. So, we found out this MA factor for rectangular beam. We also showed how the stress equation for curved beams converges to a straight beam when r, or the radius of curvature, becomes infinity. Okay? Thank you friends. Have a good day.